Hi there folks, today we're looking at similarity in right triangles, and really we're going to take right triangles, we're going to split them up into more right triangles, and pretty much everything we're going to do today revolves around this first theorem. And this first theorem, a little bit confusing when you first read it, but as soon as you see the picture it's going to make a little bit more sense. But basically, if we take an altitude to the hypotenuse, in other words, we start at the vertex where the right angle is, and we draw a perpendicular line to the hypotenuse. So we're drawing the altitude to the hypotenuse of a right triangle. What it's going to do is it's going to divide us into two more right triangles, so two smaller right triangles that are similar to the original, but they're also similar to one another. All right, so what happens here is I start with one big triangle, I split that triangle with an altitude, and it gives me two smaller triangles inside. Well, now I have three triangles, the large original triangle, and then two smaller triangles inside of that triangle. And what happens is all three of those are going to be similar to one another. And so here's what this looks like in terms of the picture. So notice I've got triangle ABC here. The altitude to the hypotenuse is right here. That's this guy. Notice I start at the vertex where the right angle is, and I go perpendicular to the hypotenuse. So that's the altitude I'm talking about, all right? None of the other altitudes will give me this because the other altitudes are the sides of a triangle. So if I draw that altitude that goes to the hypotenuse being AB, what it does is it breaks this thing into two other smaller triangles that are similar to the original, and again, also similar to each other. So like this one right here, if I take this little triangle right here, that little triangle is similar to the whole thing. And right here what I've done is I've drawn that separately, but I've kind of rotated a little bit and flipped it around so that it's in the same position as my original triangles to make this easier to see. And then the same thing with the next guy over here, this larger triangle that got split off, this one, that's also similar to the original. And again, I've kind of taken this off to the side, I've rotated a little bit and flipped it around to put it in the same position as the original to make this a little bit easier to see the similar triangles. And so what happens here is I've got three separate triangles that are all similar to one another. All right, the larger original triangle, the small triangle that is split it into, and the larger triangle that is split it into. These are all similar triangles. And the statement that I can write here, something like this: if I have triangle ABC, that's going to be similar to triangle ACD, which is also going to be similar to triangle CBD. And I just kind of write it as an extended similarity relationship. But now I could set up all kinds of different proportions between ABC and ACD, or between ABC and CBD, or between ACD and CBD. So there's a lot of information that I can come up with from this with very little information to start. And keep in mind, these are also right triangles, so we could use our Pythagorean theorem in here if we need to, but we have all kinds of proportions that we can set up. And the reason this theorem works, we're not going to go through the proof of this thing, but hopefully it's obvious when you look at this. They all have right angles, so right away I have one angle. Well then, like when I look at the original and this guy down here, I can see that they share angle A. So now because they share angle A is the same, they also each have a right angle, so the right angles are the same, they're similar by angle. Doing the same thing going over to this guy, right here they share angle B. So now I know that angle B is the same as angle B. They also share a 90-degree angle. They each have a 90-degree angle, so it's similar by angle. And then these two essentially relate by the transitive property when we start sharing all those pieces and knowing that, okay, well, all of the angles have to match up. So if they all match up to the larger triangle, then they match up to each other as well. All right, so that's where this proof kind of comes from. Relatively simple when you really start thinking about all the angles that they share. But that's how we know that these are all similar. So here's how this thing works. If I look at something like this guy, it says to find the lengths of the missing sides. So the first thing I would do, especially when we're dealing with these, is I would draw these triangles separately. Right now it gives me a lot of information, and all that information is kind of based on this triangle right here. I've got two of the sides of this triangle, so that's the one I'm going to kind of focus on. I'm going to redraw the other two, and I'm going to try to draw them in the same position, the same positioning as that triangle that I've kind of highlighted in green. So if I start with the original triangle, it's the really big one right here. I'll start by labeling A because that's where the right angle is. That's an easy one to label. And then AC is the shorter side, so that's this guy over here. And then B would be up here. All right, so I have my original, and then I have that smaller triangle. Again, I'm going to position that the same way I have the triangle that has all the information, or the vital pieces. Here's my right angle. When I look at the smaller triangle, the right angle is at D. The shorter side is CD, and the longer side, or the hypotenuse, is AC. And AC, let me try that again. And really, the two pieces that really lock this thing into place is if you know which angle it has which point represents the right angle, and then which side represents the hypotenuse. Once you label those, it should lock everything else into place, and now we should be able to start setting up some proportions. And keep in mind that I do have pieces of this thing. I already know right here that AB is 13, and I have AB over here in this triangle. That's 13. I also have AD, which is this guy. That's going to be 5. And so from there, I can start setting up some proportions. So when I compare this thing, right away, I see that this is the hypotenuse of this guy right here, and this is that shorter side of this guy. And so what's happening is I need a hypotenuse or a shorter side to match up, and I don't have that over here. See, the hypotenuse and the shorter sides are the ones that are blank, so it becomes very difficult to be able to come up with anything here. So what I'm going to do is, since I know this is a right triangle, I can find this missing side right here, BD, using my Pythagorean theorem. So that's going to be a squared plus b squared equals c squared. That's going to be a 25 plus b squared equals 169. And then I'm going to subtract the 25, so I get b squared equals 144. And now I take the square root of each side and find out that b equals 12. Technically, b equals plus or minus 12, but we toss the negative because I'm dealing with the side length of a triangle. So now I know that this is 12 inches. And knowing that piece of information, that's, let's see, BD, which I don't have in any of the other triangles, but that gives me the longer side here. So now I have things that I can compare with. So when I look at this guy, I'll just start labeling these with some variables. I'll call this X and Y and maybe Z, and how about T for the last one. Just coming up with some variables, so I'll use a lowercase t. But now I can start setting up a proportion for each of these things. If I look at the original triangle and I look at what I have, like here, this is the long side, and over here, this is the long side. So if I compare the long sides, so 13 compares to 12, well, the same way that the hypotenuse would compare, x compares to 13. So there's a proportion that allows me to solve for x. I can do the same thing with y. If I do y, I could set up the same proportion. 13 to 12 equals y compared to the shorter side, which is 5. I can do the same thing with the little triangle, the hypotenuse, which is z. But again, matching up the long sides, that's 5 compares to 12, the same way that z would compare to 13. So I'm comparing long side to long side, hypotenuse to hypotenuse. And then the same thing, 5 compares to 12, the same way that t is the short side compares to 5. All right. So now what I can do is I can just solve each of these proportions, and that'll give me each of the missing sides that I'm looking for. So here that gives me a 12x equals 169. And I'll just solve each of these simultaneously. This is a 12y equals 65. This one gives me a 12z equals 65. And this one right here gives me a 12t equals 25. And I can go ahead and solve each of these. So the first one gives me 14 and 1/12. The next one, when I plug it into the calculator, gives me 5 and 5/12. The next one, when I plug it into the calculator, also gives me 5 and 5/12. And the last one, when I plug it into the calculator, gives me a 2 and 1/12. And the interesting thing here is we have two of these that are exactly the same, and that might seem surprising at first until you really think about what they represent. Sorry, I didn't like my 12 that was written here. those represent the same side. When you look at y, it's representing AC. When you look at z, it's also representing AC. And so think about the measurements that these are actually representing. This first one is CB. So the measure of CB is 14 1/12 inches. The next one, the next two, AC, equals 5 5/12 inches. And then the last one, T, that represents CD, and that's 2 1/12 inches. Okay, so really think about what these represent, and that's why we have a little overlap there. Did we have to do each of those separately? No, we didn't, if you recognize that you're dealing with the same thing. Okay? If we look at something like this guy, this one's interesting in terms of the sides that we're given here when we start to compare these things. Because when we look at this, if I draw these two separately, and again, I'm going to draw them so that they're facing the same direction. So here I've got the little one, and then the big one. The little one, let's see, I've got a 3 here. That's the 90-degree angle. This is ACD. The larger one, I've got the 10 here, and I've got not A at all. Let me try that again. Let me start down here, and then the hypotenuse is CB. And so when you look at this, the thing that's interesting here is I have two of the sides, but not the two that I want. But there's one side that they have in common. When you look right here, CD is the same thing as CD right here. Those are overlapping pieces of this thing. So if I were to call that X, that's the altitude that I'm looking for, CD, they have that in common. Well, now if I set up this proportion, when you think about it, I've got 3 compares to X, or X compares to 3, the same way then that 10 compares to X. And so I kind of get this unique situation where I have the same variable in here twice. Well, now I can cross multiply. That's x squared equals 30. And now I can plug this into my calculator in order to find out what x equals. So when I plug that in, I get approximately 5.5. And that's going to be in centimeters. And so we kind of get this unique relationship. Instead of needing all of that information, because those two sides, we have those two sides in common, we can go from there. And really, we could have used that same information. We could have done the same thing in the last one to help us out a little bit. But with that one, we had 2 pieces of one triangle. It's easier just to do the Pythagorean theorem. So for this one, we can't really do our Pythagorean theorem because we're missing those sides. But because that one side they have in common, we can still set up a ratio that we're able to solve because I still have one variable. All right? And this brings to light a unique relationship that these things have. And so what we're going to talk about here is what we call the geometric mean. The geometric mean is just a proportion in which the means are equal. When you think about extremes and means, when we were talking about these a couple weeks ago, or a couple days ago rather, when we look at proportions, the extremes and the means, the extremes being the outside values and the means being the inside values. So we're looking at x as those mean values. When they're the same, we talk about it in terms of a geometric mean. And so that's the situation we ran into above. The means are the same. Those pieces that are across from one another are the same. So we have one set of diagonals that's the same. And so the unique relationship that we have here is that the length of the altitude to the hypotenuse of a right triangle, I'm missing the word triangle in there. So the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So in other words, when I drop this thing, and if I'm talking about the altitude as x, it splits the hypotenuse into 2 segments. Here I've got A and B. And so x is the geometric mean between them, so I can immediately set up the proportion x over a equals b over x. And I just have to make sure that the x's are across from one another. If I write it this way instead, if I have, a here and b here, I could write the x's here and here. That's saying the same thing, and we can set it up that way as well. Just make sure those x's are across from each other. That's how we represent the geometric mean. And so the altitude is the geometric mean between those 2 segments of our hypotenuse. We also have another one of these, and this one's a little bit tougher in terms of wrapping your brain around. I would highly recommend using this first corollary. This one is very, very useful, very, very simple. This one, there are some other ways we could get around having to do this, so just keep that in mind. So with this one, it says the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of the leg is the geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to the leg. Okay, so there's a lot going on there, but basically what happens is this. So I drop that altitude like I always have, and it splits the hypotenuse into two pieces. So like when I look at the entire hypotenuse here, the entire hypotenuse then would be represented by A plus B. And so when I look at the legs of the original triangle, that's X and Y here. So if I use X, if I use that leg, that's going to be my geometric mean. So it's X over the hypotenuse, that's A plus B. And then the piece that I compare it to is the piece that's touching that side. So I use A this time, so it compares to A over X. And then doing the same thing on the other side, if I use Y here as the geometric mean, so notice the Y's are across from one another. I do the ratio of the Y to the hypotenuse, and I do the ratio of this piece down here, because that's the one that's touching this leg, to that leg. So basically, I set up a proportion with each side of this thing, if you want to think of it this way. But basically, when I use this side, here's one of my proportions, X over A, or A over X, and then my other proportion would relate X to the entire hypotenuse. The other proportion that I can set up is this one, where I do Y over B, and then I compare that to the hypotenuse as well. And you just have to make sure the X's are across from each other, make sure that the Y's are across from each other. Okay? And this is a little bit easier when we see it in action. But again, this one's a little bit tough in terms of finding these pieces. We can get around this by finding other pieces first, and then going from there to find the rest of the piece of the triangle using similar triangles. But here's what this thing looks like. If I wanted to find X, Y, and Z here, I'm going to start with X because X is the easy one. That's our altitude, and the altitude relates this way. And so I'll always set up the geometric mean first. So we know that X are going to be in those diagonal positions. And then I compare them to the two pieces that the hypotenuse is split into. So like X compares to 4, and X compares to 12 in the same kind of manner. So X to 4, 12 to X. And now I can solve for that missing piece. So that's that first corollary we had. The altitude is the geometric mean between the pieces of the hypotenuse. And so now I can cross multiply here. So I get X squared equals, that's going to be a 48. And then I'm just going to be taking the square root of each side, and I'll just have to estimate that. So X equals about a 6.9. And now here's the other two. They're a little bit trickier in terms of this thing. But if I start off this way, really each of these legs can be a geometric mean. So maybe I'll start with leg Y. So if I use Y as my geometric mean, so I put Y into the appropriate positions diagonally from one another. Now the relationship is I compare that to the entire hypotenuse. And again, the entire hypotenuse over here is these two added together, so that's going to be a 16. And then I use the piece of the hypotenuse that's touching that leg. So in this case, I'm going to use the 4 because that one's touching the leg of Y. Setting up the other one, I'll set this up before I go ahead and solve these. If I use Z as the geometric mean, so here's my Z values. Once again, I put them across from each other. I compare it to the entire hypotenuse, which is 16. But then the other piece of this thing has to be the piece of the hypotenuse that's touching that leg, which in this case now is the 12th. See, and now I can solve each of these for Y and Z, and it kind of gets us around the process of having to draw all these triangles separately. But if you're going to mess this up, it might be easier just to draw the triangle separately, and that's the other option here. Once you have X, you can start relating these in terms of just the triangles and finding those pieces using the Pythagorean theorem and those kind of things. So keep in mind there are ways around this, but if you're going to use the Pythagorean theorem, don't round off this value over here. Leave it as the square root of 48. Okay? And you can simplify that, but I would just leave it as the square root of 48 as you go to do your Pythagorean theorem. And so from here, I go ahead and solve these. I'm going to cross multiply. and solve for y and z. So here I get y squared equals 64, so y equals 8. Here I get z squared equals 192, and then I take the square root of each side and find out that z equals, again, plug it into your calculator, it's approximately a 13.86. Okay, and so that's if we wanted these values, if we want to leave these in their exact format, I'll specify that, then we would just simplify those square roots, but leave them in terms of roots. And that's important if we're going to be finding other values here. I wouldn't want to take these and set up other proportions to find other values, because now I've rounded these off. And that's why it's important to leave these in terms of square roots sometimes, and then go from there. Okay? The only other thing that I might ask you to do is just to find the geometric mean between two numbers. And really, you've already done this, but it's weird when we put it in this context. Again, the geometric means these guys across from each other are exactly the same. And so the geometric mean of 4 and 9 would just be 4 and a 9 across from each other. And now I would cross multiply and solve for x. And I'd find out that x equals 6. And that's it. All right, so keep that in mind. We're doing this in context. Makes sense in terms of the geometric mean. But if I just give you two numbers and ask for the geometric mean, call the geometric mean x, set those across from each other, the other two numbers go in the other slots. Okay, that's it, and that's all there is to it.